Good afternoon, everyone. How's everyone doing? Good lunch? I was too nervous. I couldn't eat. Well, thanks for coming. My name is Ravi Gadhia. I work at GitHub. And has everyone here heard of GitHub? Anyone who hasn't? I can't comment about any of that. The acquisition has not happened yet. So something will happen someday soon, I hope. Well, if you know about GitHub, you know we're a sticker company. And I have lots of stickers up here. If anyone wants some, come see me afterward. And on our stickers, we have usually some rendition of our mascot, Mona. So Mona is half octopus, half cat. And in this rendition, you may see a tear coming down her cheek. Mona's crying. Can anyone imagine why Mona's crying?
Because you were so smart.
Yeah. That's a good, I was not, could be. In this case, Mona is crying because she's imagining a world without programmers. So that is the title of my talk, A World Without Programmers. And I'm going to spend about 50 minutes going over a topic I've been sort of researching on the side for the past year or so. In case you're curious about me and what I do, I'm a solutions engineer at GitHub. It means I work with our customers to help them understand how to use GitHub to achieve their business objectives. So that's my day job. All of this is kind of part of my night job. So let's get into it. My interest in this area started about a year ago. Our CEO, Chris Wanstrath, was at GitHub Universe, our annual user conference, and he made this statement that the future of coding is no coding at all. Right? I was not expecting this. Hearing this, I was like, excuse me, what are you talking about? We're a software company. We care about code. And if you look at the context of Chris's statements, what he said is that coding is not the main event anymore. Building software is the main event. Coding is just one small part of it, maybe the most important part of it, in my opinion, but just a part of it. We think the future of coding is no coding at all. We think autonomous coding is a very real thing. So this got me wondering about autonomous coding. Like, what is this? What is Chris talking about? And I sort of made it my personal mission to understand more about this. And so we're going to do that today. And before we get to that, I just wanted to sort of understand the scope. You know, why should we care about this? Why should we care about autonomous coding? And have you all heard of this site, Will Robots Take My Job? You should check it out. It's really interesting. It's based on work that came out of Oxford in 2013 by Frey and Osborne, where they basically wrote this paper called The Future of Employment, How Susceptible Are Jobs to Computerization? And so they predict for 702 distinct professions the likelihood that automation will make that profession redundant. Okay, so then these clever programmers codified that work into Will Robots Take My Job? They augmented it with info from the US Bureau of Labor Statistics. So you could say that it maybe applies more to the US than elsewhere, but I think it's probably broadly applicable in other places too. So according to Will Robots Take My Job, if you are a software developer of applications, you have a 4% chance of being automated out of a job, I think in the next 4 years or so. And your industry or your field is growing by 19%. Okay, so you are set to be totally safe if you're a software developer of applications. Now, if you're a computer programmer, that is someone who assists developers, builds forms, writes scripts, writes code to spec, well, then there's a 48% chance that you will be automated out. And your field is shrinking by 8%. So you should start worrying, right? If you believe Will Robots Take My Job, you should start worrying. So this is a pretty big difference, 4% and 48%. And I think intuitively, it kind of makes sense. Like the higher up you are in the food chain, the safer you are. I should point out that according to their estimates, about 47% of total US employment is at risk due to automation. This huge number. We should all start worrying if that's true. Okay, so now that we understand the scope, let's think about autonomous coding and what this is. And I started looking into it, and the first thing I realized is that, hey, no one calls it autonomous coding. So academics and research, they call it program synthesis. And the idea here is that you can automatically find a program that matches the user intent. It's been considered the holy grail of artificial intelligence since the 1950s. And I put together this agenda to introduce you all to the topic. We're going to start with a couple of examples from history. We'll go through some of the basics with program synthesis. There's a really interesting program out of DARPA called MUSE, which is related to this. And then in the final 20 minutes, we're going to go through some real-world examples of products that incorporate program synthesis within them. So with that, let's go over some history. So we're going to review two projects. One is the Programmer's Apprentice out of the MIT AI Lab. So this project was launched in the mid-70s. And their stated goal was to develop a theory of how expert programmers analyze, synthesize, modify, explain, specify, verify, and document programs. So basically every aspect of the software development process, they wanted to think about and develop some theory about. So that's pretty broad ambition given the times. Well, they scaled it back a little, and they decided to take an alternate approach, which was to intelligently assist the programmer rather than replace the programmer. And they based this, I think, on this their understanding of that at that time of how you build productive programmer teams. And there was a model that emerged out of IBM in the late 1960s. It was documented in 1971 by Harlan Mills, an IBM fellow who was like a so-called super programmer. And so Mills was tasked with writing mission-critical software of high business value for IBM. And so he developed this model where he had himself in the middle of this star. He had maybe a backup programmer to help him, and then all these other people around him assisting him, right? So this was like the chief programmer team model. And you can see he had testers and tool experts, secretaries, administrators, even a language lawyer, someone to help him with syntax issues to help decide things for him. So this is how people were productive developing software ages ago, right? Almost 50 years ago now. And so at MIT, they said, let's try to build a program that is the supporting staff. Okay, so that's what's shown here as the Apprentice. And so the Apprentice would be a program that actively interacts with the programmer, and they both interact with the programming environment, and that was the model they had in mind. They also decided to further simplify and said, hey, let's make 3 apprentices instead of 1. Let's focus one on requirements, one on design, the other on implementation, and let's keep the boundaries between these very loose so as not to stifle creativity and innovation. And some of the outcomes, they identified that they needed some basic things for a system like this. They needed a way to represent structure and function. They needed a way to reason about change. And then they needed a library of that encapsulated all of their techniques around programming. So they developed this thing called Cake. It's like layered system to represent knowledge and reason. So you can see there's like at the bottom propositional logic, algebraic reasoning, so logical reasoning, arithmetic reasoning. Frames was like inheritance and structure, and the plan calculus, this is kind of getting to your algorithms in your code. They had this thing they called the plan calculus, which was a set of overlays. Here's an example of an overlay. And on the right-hand side, you see the specification for an operation. On the left-hand side, you see the implementation. So it's kind of like a flow chart with data types and data flow embedded, right? So they invented all of this stuff for the purposes of their research. And some of the outcomes, they had 3 apprentices, an implementation apprentice, design, and requirements. So implementation focused on business data processing in Ada and Lisp. Design was device drivers in Lisp. And requirements was like inventory tracking systems. Okay, so without going into the details on these things, let's look at some of the commonalities. So you can see that for each, they chose a very specific domain, right? So they realized they couldn't boil the ocean, and they picked something that was very targeted that they could potentially boil. They also used very highly constrained spec languages for each. They used their system of cliche libraries and cake, and they had simulated user interface and user experience. So even though they had really ambitious goals, they, in the end, pared down to something that was achievable. And as an example, the implementation apprentice converted a 5-line spec to 55 lines of ADA. Okay, so that's what one of the examples of one of the things they were able to achieve. And they discovered that there's a fundamental trade-off with automation of programming, that the generality of your specification language is proportional to the difficulty of automatic implementation, right? So the more general your spec, the harder it is to do what you want to do. All right, the second example I wanted to share with you is the NASA Amphion project. This is out of NASA in the mid-90s. It's part of their knowledge-based software engineering group. And their goals were to enable end users to write programs without writing programs, but by writing specs and then have the system synthesize the program. They wanted the system to be generic and extensible so that you could easily modify it for different domains. Okay. Anyone recognize the image? The planet is Saturn, yes, and the spacecraft is Cassini. So they had an implementation of this Amphion project that was targeting solar system exploration. It's part of the Navigation and Ancillary Information Facility, NAIF. And so what you see here on the left-hand side is the input to the system, the specification. On the right-hand side is Fortran 77 code. Okay, so the graphic on the top left, if you can read it, it has on the left-hand side, it says time coordinate. So that is the input to the system. It's the time and coordinate on Earth. And on the top right is angle in radians. That's the output of the program or the specification. And so what I believe this is, I believe this represents the angle or the phase of the moon given a time on Earth. And so you'll see there's a separation angle exposed on the top, and that's the angle between the array from the moon to the Earth and array from the moon to the sun. So they had a GUI that helped the end users define the graphical spec. That was translated to the text-based spec that you see on the bottom, and the system took that as input and generated Fortran 77. Okay. And so here's a diagram of their system. You'll see on the left side, it's the domain-specific part. And so it takes a domain theory that feeds into the interface. It also feeds into this thing called SNARK. SNARK is a theorem solver. So basically, they're basically taking something that's generalized and making it domain-specific. Now, in the top right, you see the specification acquisition subsystem. So the user is interacting with the GUI to generate a formal spec. That spec is checked for correctness, for solvability. Is it over-constrained? Is it under-constrained? And the user kind of can iterate back through that loop. Eventually, the spec is fed into SNARK. And SNARK goes through a process of determining the applicative program. And as I understand that process, they would take all of the constraints and rules that were in the spec and axiomatize. So looking for other true statements based on those. And some of those axioms were very abstract. Others were implementation oriented. So they eventually were able to distill it to a set of implementation axioms that were the program. And they convert that then to the Fortran code. Okay, so this is the system they built. And it worked. So here's a visualization for Cassini, where you see on the bottom left, you can probably barely read it, but you have Cassini in the bottom left, and you have the sun on the top right, Saturn's in the middle, Titan's sort of on the bottom. They supplemented this to have a camera. Okay, so this is the problem that they're feeding into the Amphion system. And the system generated some code. So here's a visualization generated by by Amphion. Let's see, did that not play? Let's see if that plays. There we go. So this is a flyby of Cassini flying by Saturn, and we saw Titan go by. So that was done years before the spacecraft ever got there. They were trying to help the scientists plan for the observations they were going to make, right? That's pretty cool considering that's now, what, almost 25 years ago. So those are two examples that I hope will give you some sense of what we've been able to do with program synthesis or autonomous coding in the past. Now let's look at some of the basics. So you can think of program synthesis as the problem of finding a program that within a specific program space matches some user intent. Okay, so the synthesizer here is shown in the blue blocks, and it's conducting search over the program space based on the user intent. And there's two main challenges. The first is the intractability of the program space. Right? If you think about all the programming languages out there and the set of possible programs that could be written, it's massive. Right? There's no way that anyone could do like a brute force synthesis technique and actually find something in anyone's lifetime. Right? So the space is huge. The other challenge is the diversity of user intent. Like how you express your intent, and then how the synthesizer would take that and do something meaningful with it. So let's go through this in a little bit more detail. All right, so user intent, and maybe we can crowdsource this a little bit. Can anyone think of ways that I would specify my intent for the program I want to a synthesis system? We've seen one so far, which is it was a spec, right? A spec being fed into the Amphion system. The blue circle on the bottom will give you a hint. Speak, right? So natural language is another way. We could provide assertions, right? Assertions are conditions that must be true for the output program. We could give it tests. Like if you think about test-driven development, if you're going to write the test first before you write the code, why even write the code? Have the system write the code. You could feed input-output examples, right? For this set of inputs, write code that will give me this set of outputs, and make it not a case statement, for example. Trace is basically similar to input-output examples, except it's sort of you follow the inputs as they're transformed into the outputs. Demonstration is a novel one. You could take a similar program and record yourself using it, and then use that recording as the input to the system. Or maybe you give it a related program or multiple related programs. You could give it a partial program. Like I'm going to write all my code except for the part I don't understand and just leave a big hole there. Right? So that's called a sketch. You could give it a template, which is more of like a syntactic hint of some of the syntax of the output program. Maybe if your program has a GUI, you want to give it an image. And the last one I think is the most compelling, a combination of all of these. Right? I would love to tell my synthesizer to, hey, take this program, change these things, slap this GUI on it. That would be like, to me, that's the obvious one, a combination. So there's so many ways of specifying user intent. And so if you're building a synthesizer, you need to figure out which one of these you're going to support. All right, let's talk about program space. So for the synthesizer developer, the person building the system, they need to find a way to constrain the search space so it's expressive enough to generate meaningful programs, but constrained enough to allow for efficient search. And so to give you an idea of like how bad the problem can be in terms of the size of the space, there was a talk given 3 years back by Rostislav Bodik, and he there mentioned that to discover an expert implementation of the MD5 hash function would require exploration of a space of 10 to the 5,943 programs. So like 10 and 6,000 programs, right? You can't go through that enumeratively. You have to find some way of pruning down the space. Okay, so there are some techniques for constraining the program space. If you're using a functional or imperative language, a common technique is to reduce or restrict the operator set. You can also restrict the control structure. Like maybe you're not going to use all types of loops, but use enough that you could still implement anything you want. You could construct a DSL or choose an off-the-shelf existing DSL that meets the requirements of your domain. You could use a grammar as a way of restricting the kinds of statements that could be in your output program. Or maybe your output is not actually a program itself, but a logical representation that could be then further transformed into a program. So there's lots of ways to constrain the space to make the synthesis task more efficient. Okay, so and then we talked about the synthesizer performing search over the space. There's also a variety of search techniques, and here are just some like broad buckets of techniques. Right, you could do a enumerative search, which is the bottom-up approach. That doesn't scale. That only really works if you're dealing with like small code fragments. Right, if you're dealing with large programs, enumeration will lead to too many combinations. Right. With deductive, the idea with deductive is to recursively reduce the spec into simpler sub-problems. So you could imagine having like the spec for your program that's quite complex, and as you reduce it into simpler sub-problems, at some point each of those could be maybe code fragments that you could then enumerate and do bottom-up. Right? So you can already see that doing top-down and bottom-up in combination might be effective. There's a whole there's a whole group of people who are using logical reasoning approaches to search and synthesis. And so the idea here is to, based on your input spec, you generate constraints and then you solve for those constraints. And so there are like off-the-shelf solvers, SMT solvers, SAT solvers. I've read about these things. I know very little about what's actually under the hood. But the idea then is to generate a set of constraints and then simplify them into something that could be solved by an off-the-shelf solver. And then there's a whole bunch of statistical mechanisms or techniques, machine learning, genetic programming, sampling. These are obviously driven by the latest wave of big data analytics. And then again, at the bottom, combination. In most systems I've seen, they're using all of these or multiple techniques. So I just want to crystallize what we've just talked about by going through a couple of real systems. Okay, so the one you're seeing here is the block diagram of something called counterexample guided inductive synthesis. And this picture is lifted from the PhD thesis of Armando Solar Lezama, who was at UC Berkeley in 2008. And he's at MIT now and doing similar type of work. But this was seen as, in a way, groundbreaking, because through his system, he sort of smashed all of the records of all the benchmarks. And so what he's done, he's built basically, in CEGIS, you have a sketch. So a sketch is a program with holes in it coming in. You also have input-output examples. And so if you think about input-output examples, if you have like a whole ton of input-output examples, each of those represents a constraint, right? And the more of those you have, the more complexity the synthesizer needs to handle. So his approach was to, instead of giving the synthesizer all of those examples, let's just take some small representative set, right? So handle the common case, handle the corner cases, and that's enough input-output examples to actually generate the program that's going to satisfy everything. So his inductive synthesizer would basically use like solver techniques and generate a candidate implementation. A checker would then check against all of the other data points, and if it found a failing one, cycle that back. And so by iterating through this loop, they would converge on a candidate program that actually passed and got the OK. So that's the basic idea with CEGIS. Here's another example of programming by examples. This is taken from a paper by Sumit Galwani at Microsoft Research. And in programming by examples, you basically use examples to express the intent. And then the system is also provided a DSL, so it's now constraining the space through a DSL. You give it a ranking function so it can score, and then basically it's going to come up with a ranked set of programs. In the debugger section, this is where the user gets to provide feedback. And then based on that refined intent, you iterate through, and eventually you get your intended program that you can then translate. Okay, so these are two examples of real systems that can perform program synthesis today. And before I move on, I'll just mention about programming by examples and contrast it to machine learning, right? So with programming by examples, you're using very few examples. The output is more or less human readable, and it's like small scripts, right? Machine learning uses many examples. The thing that it creates is a black box, and it can be very, very sophisticated. So it's possible that you could use machine learning in some synthesis applications. And in fact, we're going to see examples of that. But with programming by examples, it's kind of designed for a scenario where you have like very few or almost no examples. Okay. All right, so again, just to sort of recap, we've got 3 dimensions in program synthesis, as Galwani has sort of talks about it. Program space, user intent, and your search techniques. You've got to have a ability for the user to specify what they want. You've got to constrain the program space so that it's efficient to search. And then you have to have a search technique that's going to match the two. I think there's a 4th dimension, value. The impact on humanity, impact on scientific research. So these are the things I think about when I come across a new tool or new product in this space. All right, so we're going to now talk about this program at DARPA called MUSE. So DARPA, if you have heard of it, I'm sure you have. It's the Defense Advanced Research and Project Agency. It's like the funding arm of the Department of Defense. They have funded a lot of great stuff. Like, I mean, besides the controversial stuff, DARPA used to be called ARPA. ARPANET was the precursor to the internet, right? The first packet switching network that implemented TCP/IP. So DARPA these days is thinking about software. And for the past 4 years, they funded a project or a program called MUSE. And the premise of MUSE was to take big data analytics and techniques therein and apply that to the corpus of open source software. Okay, and they funded multiple research teams. They just concluded MUSE, I think, a couple of weeks ago. They had the final PI meeting, and I was lucky enough to attend. And so within MUSE, they basically, they have this massive corpus of open source software, and they're basically encouraging the researchers there to build out solutions in 3 major application areas: program synthesis, automated bug detection and repair, and code mining and semantic search. So though this talk is about program synthesis, I'll just impress upon you that all 3 of these areas are very interrelated. Okay, and I'll just try to argue why. If you think about automated bug detection and repair, right? If I have a massive corpus of data, it's conceivable that I could use statistical techniques to identify like commonalities for API usage for a given API. And I might be able to identify cases where someone is doing something that looks wrong because it's not the common approach. So maybe I'm going to flag that as a potential bug, right? So I've then detected a bug. I could use statistical techniques to also suggest repairs. Okay, so if I think about program synthesis, and one of the input modalities was to provide a sketch, right? That's a program with a hole in it. That's very similar to a program that has had a line removed because it looks like a bug, right? So some of the things that we're building for automated bug detection and repair absolutely apply to program synthesis and vice versa. this is just a sort of a depiction of all of the data in their corpus. It's 11 terabytes and growing. This slide is just titles of some of the research projects they're doing. I've read about some of these, not all of them, but they have a pretty handy site. It's the MUSE portal. I think it's muse-portal.net that you can go check out. And so I went to check it out and see what was there. And I think we have an animation that was going to play here and kind of show you all what's there. So they have the 3 different areas, bug detection and repair, code mining, and synthesis. And within each area, there's a bunch of projects. You can click on them to read more. The one that's most applicable to this talk is a project called Bayou, where they're using, I think they call it neural sketch synthesis, to generate Java programs based on some search string specified by the user. And so if you go to Bayou now, you can actually do this. And any Java programmers here? Yeah, OK, so I'd be curious if you check this out, how useful you think this is. So you basically specify a search string where you can specify types and methods to be called. And then you basically click search, and it's going to give you applications or programs that satisfy your search string. OK, so I just did the default here file read, and it's going to generate for me examples of programs that have the call read line and the types file reader and buffered reader. OK, so and you can see that on the right. It only took a few seconds, right? So that's, I think, pretty impressive that it can do that. And also they have numerous examples. So if the example they've given you doesn't actually meet what you're looking for, you could cycle through a few more. Okay, so that's one example of a prototype system that potentially has some applicability or usability for users or even students. So now let's go through the real world examples in products. We're going to go through 3 areas: assisted development, followed by front-end design, and then data wrangling. Okay, so this is, Microsoft is a big sponsor here. A lot of .NET developers and users down in Australia. I would be remiss if I didn't talk about IntelliSense. So IntelliSense has been around a long time. First introduced in 1996. It became more powerful in 2001. It was on by default in 2005. In 2016, there was something called the Developer Assistant plugin, which didn't seem to go very well. I don't know if any of you all used it, but the idea with the Developer Assistant plugin was to do more of a contextual search and to provide the programmers with even more assistance. Okay, people said it was a neat idea, but clobbered IntelliSense, that it made IntelliSense choppy. And the idea was, as you're typing code, instead of just doing the standard code completion that we're all used to, with this Developer Assistant plugin, you would then be shown, given the opportunity to ask, how do I do something, and be shown code samples. And while this might be really good for the novice or junior developer, it sounds like for experienced developers that this was really a hindrance, right? So Developer Assistant didn't really fly. But then earlier this year, in May, Microsoft announced Intellicode. And it seems to refer to a set of capabilities that leverage AI-type techniques to enhance the developer experience. And I mean, so far, it's pretty cool. I have a little short video here that shows that when you install Intellicode, IntelliSense is now not just giving you results in alphabetical order. It's giving you suggestions based on the context, right? So they've apparently trained the AI against thousands of open source projects with hundreds of stars each, right? So they're high quality projects. And so you're seeing that the completion and the overloads, all of that is sorted by relevance rather than alphabetically. There are some other things that they're introducing, they have this editor config file where you can infer the coding conventions for your code, for your data set, for your code, and then you can apply it to all future additions to your code base. And then they've also blogged about doing more, like having Intellicode comment within pull requests and suggest changes and highlight files of interest within pull requests. So clearly a lot more is coming with Intellicode. And I wrote to the PMs for Intellicode trying to get some articulation of what the vision was. And they were rightly very secretive about what they're doing. There's another outfit out of Europe, deepcode.ai. Has anyone tried this? No, I made the mistake of Googling this, and now it's like showing up on my Facebook. But basically, with Deepcode, you can enable Deepcode to look at your repositories on GitHub and perhaps elsewhere. And when you do that, it's basically going to look at your code, compare it against a lot of other code that it's looked at, and then highlight potential problems and suggest fixes. Right? So I've just given it access to the Bayou repo, the one from MUSE, and it's suggesting, you see in red, it's flagging potential errors or potential bugs. It's telling me how many repositories that suggestion is based on, and then it's giving me some like helpful links for supporting information, as well as allowing me to sort of go through the code. Right, so this is clearly in the developer assistant area. And if you read Deepcode's blogs and all of the commentary around them, they talk about program synthesis as the future of where they're going. Right, so clearly they're aimed at something more than just bug detection and repair. So it'll be really interesting to see what comes out from these guys. And then the third one here, GitHub just announced earlier this week, we have an experiments site now. It's called GitHub Experiments. I think experiments.github.com. And the first experiment that we've released there is semantic search. So this is something that one of our smart developers has put together. And my understanding is that this is a prototype, but it basically allows you to conduct search using human language. Right? So if you're looking for a solution that, well, this is really washed out, so you can't see it. But normally, when you're searching for code, it's very difficult to find code based on a description of what you want or what it should do, because classical search is just based on what's in the repository. So unless there's documentation that matches what you're searching for, you're not going to find what you want. So the idea here is to extract the semantics of what the code is doing and to have that in some kind of searchable index that you can then search through using human words. And there is a blog post if you want to read about what is going on under the hood with that one. All right, so we're going to now turn towards some examples in the area of front-end design. Has anyone heard of Pixtocode? No, Pixtocode, this was published in May of 2017, so like a year and a half ago. A guy, Tony Beltramelli, based in Copenhagen, he basically talked about this tool he had put together to optimize front-end work. Okay, so trying to improve the iterative capability between the user interface and the front-end developer. Okay, so I chatted with him a couple of weeks ago, and he explained to me that earlier in his career, he was involved in a lot of front-end work, and he grew frustrated because there was a lot of redundancy, right? So there's this process when you're doing front-end work where you might start with a sketch of your interface, like maybe the product manager is putting this together, hands it off to the front-end team, and the designer is then going to lay out an interface, design the interface. The developer is then going to implement that and implement features, and you just iterate through this. And every iteration, there's all this redundant work. And so then Tony decided that he would build a system that eliminated that redundancy. And so he came up with Pixtocode, which has now formed the basis for their company called Wizard. So you start with a drawing of your wireframe. You give it to the system, and it generates your iOS storyboard in Xcode, or your Android app, or your web app. And it is pretty slick. So here are some screenshots where on the left is the picture, on the right is the storyboard. Same thing for web. and he sent me this little short video describing, or at least showing the system in action, where he's uploading, did that work? Yeah, uploading 2 images to Wizard, and within seconds, Wizard is generating the associated the preview mockups as well as the code. So the question is, how does it do it? What's under the hood, right? So you all are not experts, but you've had like some introduction now to synthesis. Let's sort of think about what they've done with Pixtocode to better understand how synthesis works. So they're basically going from a drawing to a program. And can anyone think about what's in between? All right, I'll give you a hint that they're not going to a program. They're actually going to this, which is a representation of the drawing. Okay? So that's a textual representation of the image on the left. And what that means is that they're actually using a DSL. The program space is the DSL for describing user interfaces using text. That output text, which represents the user interface, is then translated. They have these 3 compilers, one for web, iOS, and Android. So really what the synthesizer is here, it's a trained deep neural network. And the training data is pairs of sketches and these textual representation of that sketch. Right? So this is all on Tony's GitHub repo. And this was really innovative, really novel. This changed like the way people thought about front-end design. And since then, since Pixtocode, there's been all these other groups are now doing very similar things. So there were Ben Wilkins and a few folks at Airbnb. They built a prototype system that did something very similar. So there's a very interesting blog on this. And it sounds like this was a prototype that never really got productized, but they built this very quickly as a follow-on activity from after reading about Tony's work and other similar work. Emil Wallner has taken the same idea and applied it to Keras. And so there he's going from screenshot to web app using the same, I believe the same data set that Tony used, perhaps with some modification. There's an outfit out of Europe, Teleport HQ, where instead of going from a drawing, they're going from an application called Sketch. And so they've built a plugin for Sketch so that whatever is being sketched gets pushed out to their system, which is then synthesizing everything on the back end. And then lastly, Microsoft recently announced something called Sketch to Code. I think maybe 3 weeks ago it came out. And the idea here is that this is like a SaaS service built on Azure, where you can basically upload a drawing, and it's going to generate your HTML for you. I asked Tony whether he was worried about this, right? Like, who wants to compete with Microsoft? And his view is that this is probably more of a way of driving Azure than competing with his company directly. But it does show that there's a lot of opportunity in this space, right? To really optimize and make front-end designers more productive. Right, so moving on, here's just a block diagram of what's under the hood with Sketch to Code. And you'll see that it's clearly just driven off of all Azure services, and rightfully so. Okay, so the last area of real-world examples, programming by example. And we had a picture earlier. This is a prettier version of it. It describes something called PROSE, Programming Synthesis Using Examples. There's a research group at Microsoft. It's probably the biggest group of program synthesis experts in the world. And they've put together this system where they're basically they're taking the fundamental technology within PROSE and applying it across all of Microsoft products, one by one. And they've also optimized where they can using state-of-the-art techniques. So for the synthesis framework itself, they've enhanced the search, top-down search using machine learning. They've also enhanced the ranking functions using machine learning. And the details are really interesting, but we don't have time to go into that here. But I did want to show you Excel. This, I would say, is probably the instance of program synthesis that has had the biggest impact and the broadest reach on humanity so far, which is the flash fill feature of Excel. Has anyone used this? Yeah, yeah. So it's cool, right? So you have a column, and you want to derive another column based on it. All you have to do is like give an example, maybe 2, hit Control-E, and Excel will populate the rest for you. And if there's a mistake in what it populates, you just correct it, and then it auto adjusts. So what's happening, this is program synthesis under the hood, where Excel is now generating macros based on your examples. Right? Who's ever written an Excel macro? Okay, so you guys have. So you don't have to do that anymore, potentially, if it's just some kind of basic string manipulation, right? So that's flash fill for Excel. There's another example. Apparently, there's the Azure ML Workbench. And if you sign up for that, you get access as a data scientist to data wrangling capabilities. And I have screenshots here, as well as I sort of went and I got a version of this from the folks at Microsoft. And so basically, it's if you're a data scientist and you're trying to prepare your data or clean your data or wrangle your data in some way, you could write code to do this, Python or whatever, or you could use a tool like this, where you can read in your CSV file or whatever your input file is, and the tool then tries to figure out for you, what should my delimiters be, what are my separators, and then it's also going to it shows you all the columns. It will infer all of the data types for each of the columns as well, give you the opportunity to adjust. You can do some sampling if the data set is massive. And you can include the path of the file if you care about that. All right, so I'm opening this. And this is a 911 call log. And so I'm just going to show this video two features of this tool that are very relevant. And if I right-click, you may see at the top it says derive column by example, split column by example. So it's basically using programming by examples, where you give maybe 1 or even 0 examples, and the tool will guess the correct code and instantiate that for you. Okay, so in the first one here, you see I have a timestamp, which is just a string timestamp. And I know that December 10th is a Thursday, and I want to convert the date to the day of the week. And I want to take the time, which is 17:10, and say it's 5 p.m. And you see the system thinking, and it's gone off and written the code that implements that for all of the rest of the rows. Okay, that took 10 seconds. So there's an advanced mode where it allows me to give more examples. And then as the next one, I'm going to split by example. Let's see if I do that. And I guess the other nice thing about this tool is that it gives you all the steps on the right-hand side. So if you're a data scientist and you want to know, how did I get to this data set, it's all recorded there for you. When you save, you're saving not only the data, but all of the steps as well. So in this instance, I am splitting by example. Right? And it did the split I wanted. I wanted to split on the semicolon. But if you look, I don't have any examples. So the tool actually guessed what I wanted without me telling it what I wanted to do. So that's the direction they're going in. They're trying to make PROSE very predictive and not just responsive to example. Okay, so hopefully that gave you some sense of like where is autonomous coding in the world today? Where are we seeing it? And looking ahead, folks at MIT are revisiting the Programmer's Apprentice, by the way, because a lot has changed, right? Computer science has changed. Computers are like 50,000 times more powerful than they were back when they started the project. We have all of these new techniques in natural language processing, machine learning, analysis, theorem proving. We have GitHub, we have Azure DevOps, we have all of these things that didn't exist before. And so clearly it's a new opportunity to re-examine some of the challenges of the past. So in my view, I think today we have program synthesis available in sort of very narrow domains. The code being generated really is still just like fragments and snippets as shown in the programming by examples example. And we're seeing that machine learning is really being impactful, right? Machine learning is responsible for all of the front end innovation that's happened in the last year and a half. But I think going forward the next 1 to 3 years, we're going to see a lot of new capabilities that are emerging in bug detection and repair, maintainability of software, maintaining for performance and security, optimizing over time, summarizing code, semantic search. All of these are just going to be exploding areas in the next few years. I expect to see stuff like that on GitHub, though I'm not deeply involved with that. I would think that we're going to be doing a lot in that area. And then at some point, maybe 3 years out, we're going to see programmers, assistants that are more than just a suggestion in a pull request, but maybe someone that's really seems like a person coding alongside me, like a team member, a virtual team member living in, either in my ID or somewhere in the cloud, really actively helping. So, if you're thinking about a world without programmers and, worried about getting automated out, my personal view is that we have plenty of time, and but Sumit Galwani, he thinks that like program synthesis and programming by examples explicitly is how we're going to be programming the robots that help us and serve us, right? We're going to be showing them what to do, and they're going to be writing code based on those examples. That is programming by examples. And Tony Beltramelli, he thinks that the rising tide lifts all ships, and that as tools advance, people will advance too. And so, I'd say we have plenty of time, and we shouldn't really worry about robots taking our jobs yet. So, thanks everyone. Any questions or comments? Yes. Mm-hmm.
Finds a problem with what you've done. The other scenario is it writes something that's presumably not supposed to be human readable. It's writing some code that you're not going to then start modifying. So in that case, whatever you start out with, whatever language you're going to use to describe the requirements, can't you just think of that as now a high-level language? So all you're doing is replacing a high-level language, which is the language of the requirements.
That's interesting. So your notion is to have a new way of speccing that is actually represents the program itself. If it's going to be translated then to something that's not human readable, then the
Surely what you're doing anyway, because there has to be some way that you specify what the requirements are. There has to be some way you tell it in order to produce the program. So whatever that is, that's your new language. You've just created a high-level language.
and this is if you actually try to do it that way, the input language then could be as complex as the output language, right? So I think that's one of the challenges as well, is that the complexity of developing the spec can match the complexity of writing the code, right? Yeah, or at least designing that language. Yeah, that's a good point. Anyone else? No? Well, thanks for coming, and see you at PubCon perhaps tonight.